Welcome to problem solving session for computational commutative algebra. I am Siddhi Balhumburi from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 11. That is problems related to graded rings, projective space of graded rings, homogenization and free resolution. So let us start with the first problem. So let K be algebraically closed field, then we have to find the Proj of K x comma y. Okay, so this is our first question. I hope I'm audible and visible, right? Please let me know if that's not the case. So yeah, so we have to find the projective space or proj of this polynomial ring kxy over algebraically closed field K. Okay, so let us first go through the definition of this proj here. So if K is a field and S is this polynomial ring in n plus 1 variables, so x naught to xn, so there are n plus 1 variables with the degree of xi is 1 for all I. So this is standard grading over the over polynomial ring S, and this M is our unique homogeneous maximal ideal in this polynomial ring. Then this Proj S is subset of spec of S, and it is collection of all those prime ideals P of X such that P is homogeneous and P is properly contained in this unique homogeneous maximal ideal, that is ideal generated by the variables. So this is the definition of Proj, and since this is subset of spec, recall that spec S, in spec S, if I is an ideal, then this V of I is actually all those prime ideals in spec S such that I is contained in those P. Collection of all ideals, all prime ideals which contain that ideal I. So that's how we define this ideal I. Also for any element F in S, we have this set defined DF. Again, this is also subset of, it is also, so this is just complement of this VF. So what is VF? VF is collection of all the prime ideals such that F is contained in P. So DF is what? It is complement of VF. So it will be P in spec S such that F is not contained in this prime ideal P. Okay, and we also have that these two things, that VI is isomorphic to spec of S mod I. So remember, all the ideals in S mod I are ideals containing I mean the non-zero ideals. So the spec of this S quotient ring S mod I is all the prime ideals which contain I. So these are precisely prime ideals in VI. So this isomorphism, we have seen this, and DF is isomorphic to spec of SF, localization of S at F. So where the multiplicative set, so multiplicative set here is this 1F, F square, and so on. Okay. So similar to this, we have this analogy in Proj S. So in spec S, I was any ideal. Okay, so but in this case, I need I to be homogeneous ideal So we are only talking about homogeneous ideal or also graded ideals. And in this case, again, we can define this Vi in Proj again the same way, that all those P in Proj S such that I is contained in P. And similarly for any F in S, F is homogeneous. Again, my element F which I am choosing is, and here instead of D, we define it to be UF, which is again complement of this VF in Proj again. And it is all those P in Proj S such that F is not contained in P. And once I have this P in Proj, it is homogeneous prime ideal. And it is also, P is not equal to the maximal ideal, unique maximal homogeneous ideal, that was the ideal generated by all the variables. Okay, and similar to these isomorphisms we have, here also we have this V of I is isomorphic to now Proj of S mod I, this quotient ring. And again, this UF is isomorphic to Proj of SF. And so this is some, what I can say, uh, I was recalling few things that how the specs and Projes are have the similarities. So we have to now find Proj of this K XY. So we already know this, right? That dimension. So now going back to finding Proj of K x comma Y. Okay, we have to find this. That what is this? Okay, so we already know that dimension of this K x comma Y is 2. Okay, and this Proj S. So if I let me call this S to be K x comma Y, then Proj is all those P in spec of S such that P homogeneous. I'm just repeating the definition. And P is now properly contained in M. Okay, or P is not equal to M. Okay, so note that M is maximal ideal. M is this ideal, x comma y. And height of M is 2. We know this, right? Because we have this chain 0 contained in x comma y. And we can't plug in any element in between. So height of this maximal ideal is 2. And we have this P properly contained in M. So this height of this prime ideal must be less than 2. Okay, so Proj S, then this set again. Here instead of writing this, I can just write this P in, oops, not, yes, it is correct. Spec S such that P is homogeneous, that is okay. But instead of writing this P not equal to M, I can say that height of P not equal to 2. But what does that mean? That height of P is less than 2 because dimension of kxy is 2. So the chain, uh, maximum size of the chain of prime ideals will have size 2. So that's why I can write this set Proj like this. Okay, so since height of P, that's why, okay, this P here. So since height of P is now uh, less than 2, so this implies that height of P is either 0 or height of P is either 1. Okay, so case where height of P is 0, so we want height 0 prime ideals. So height 0 prime ideals means what? These are all, it means P is minimal prime in S. But S is what? S is integral domain. So therefore 0 is a prime ideal and 0 is also minimal prime ideal. So therefore in height 0 case, my P is just 0. P is just ideal generated by 0. Is this okay so far? That how things are going? So height 0 prime ideals are only are minimal ideals because there is no other prime ideal contained inside that prime ideal P. Because if that is the case, then that Q which is contained inside P properly will give me chain of height 1 for this P. So height of P becomes at least greater than equal to 1 in that case. So if I say that some ideal is height 0 prime ideal, then that prime ideal becomes minimal prime ideal. So I hope that much is okay. Then now we have to deal with this second part. So that is P, height P is 1. So if you remember last time, we solved one question where we prove that if I is a integral domain, if R is an integral domain and I is height 1 prime ideal in that integral domain, then P will be a principal ideal. So height 1 prime ideals in an integral domain are principal ideals. I think we were in UFD in that case. Yeah, we had R to be UFD and we had height of prime ideal to be 1, then in that case we proved that P will be a principal ideal. Okay, and here we are in KXY, so which is again a UFD. So, and K is also algebraically closed and so on. So that's not a problem. So this implies that P is principal ideal. So let me write this from last week. We have that in UFD, height 1 prime ideals are principal ideal. Okay, so this is what we did last time. So therefore, P is some F where F is again homogeneous because P are homogeneous here. Okay, P are in Proj S, and I mean we are finding how the Proj S look like, and we are dealing with this P in space such that P are homogeneous and they have height less than 2. So this P is a homogeneous. So F is an homogeneous element. Is a homogeneous element. Okay, so it means that F belongs to some graded component, only one of the graded components. So it is homogeneous. So all the elements of F has same degree. Okay, so F belongs to some, let me write it in the words. It belongs to some graded component of S, or yes, which was our KXY. Okay, so we have this S is equal to I from 0 to, or I just belong to N, S, I. Okay, so this F is a homogeneous element, so it belongs to one of the degree component of F. Okay, so but once I have this, that suppose F belongs to some SD. Okay, that is D, degree D component of S. If you have any doubt, please let me know. Okay? And you can stop me in between to clear out those things. So far we have this. So that degree D component of F is in degree D component of S. So F will be what? It will be some summation Cij x power I y power j, since we are in two variables, such that this I plus j is D. Is this okay? I mean, how this F looks like? Is there any problem here? If not, then I will move. Okay. Okay. Please let me know if there is any problem. So far this is clear, right? So F, I can write it in the form like this, where I plus D is 0. So Cij's could be 0 in between to avoid the terms which are not there in F. So in general, it looks like this, and where this Cij, let me just write this, that it is belong to this uh, field which we started with. So if I divide this F by, so in general, any homogeneous so okay, in general, any homogeneous polynomial in two variables can always be written as product of linear factors. So when I say linear factors or linear forms or linear uh, factors in S are of the form this ax plus by. Okay, these are my linear forms where this ab in okay, that's okay. But this you know, right, that any f which is a homogeneous polynomial, it can be written as uh, linear forms of this kind. I mean, it goes like this, that if f is some summation Cij x power I y power j, where I plus j is d, then I divide by y power d. So it becomes f by y power d. And then it is summation I plus j from it. This remains as it is. This doesn't change. And when I divide by y power d to right hand side, this becomes x power I. And here it is what? Y power j by y power d. But then this becomes y power I together. Okay, because I plus j is d. So let me just write this. And then this becomes summation I plus j, Cij x power I. And again, this is y power I. So this becomes x by y power I. And now this is the polynomial. This is the polynomial in. So this I can look at it as some polynomial in kx by y, where I treat this x by y as a single variable and k is a algebraically closed field. So I can split this Cij. Okay, this is not correct. This is not completely correct. In a algebraically closed field. Yeah, 2 over algebraically closed field. Yes. So then, so this is my polynomial in one variable. I can treat this x by y as one variable, and it will be some polynomial, and it will split in a linear form in my this field k, this new ring, and then I will get it some. It will be of this form, x minus not x but x by y minus alpha 1, so on, and x minus some alpha j, something of this sort, x by y. And then when I multiply everything on the right hand side, I get this. It will be some k here, alpha k, and this x minus alpha y, alpha 1y, x minus alpha ky, and everything. This is y power k into y power d. I'm now again taking this y on the other side, and it will be, and this k will be less than, what I can say, this k will be less than d, okay, less than equal to d. Because see, here this polynomial, in x by yi, this I is less than equal to d, okay, because I plus j is d, so I is less than equal to d always. So this y power k, this k which I am getting here, this, let me write this as a small, not this k, not k, some other m, let me write it as m, m, m. Here m is less than equal to d, okay. I mean, I hope you understand why this is the case. Then f is some x minus alpha 1y, so on, x minus alpha my, and this will be some y power, doesn't matter, y power d minus m. And this is still a linear form, okay. This is linear form of the type x minus 1 only y, and so on. So in short, I can just write this f as linear factors in kxy. I hope that much is clear. So in general, instead of writing like this, suppose, so this f is therefore of the form some, so in general, f is equal to some a1x, mm, a1x plus b1y, sorry, a2x plus b2y, so on, some akx plus bky. Okay, I mean, instead of writing this, I'm just writing it in the general form. That doesn't matter. I hope I'm still audible and visible. Hello? Yeah, so instead of writing this f as x minus alpha 1 and so on, I'm writing this f in general form. Okay, so this explanation is just to, I mean, this part is just to explain you that yes, f can be written as linear form in cxy, as a product of linear forms in cxy, and I'm considering this f to be like this. But since f is prime, this implies that f will be one of this. F will be generated by one of, I mean, f will be one of these terms. Okay, so let us, let it be this ax plus by for some a comma b in k. So if I start with some height 1 prime ideal in Proj S, I end up getting that this P is ideal generated by ax plus by. Okay, so what can I say from here? That then if, so where this a comma b is in K2. Okay, A and B are from K, so I can just write AB in K2. So, and note that this AB are not 0, 0 because height of P is 1. Okay, we are, if it is 0, 0, then height P becomes 0 because 0 is prime ideal in KXY. So therefore we get this one-to-one correspondence between this P in Proj K x comma y minus 0, okay, and with this a comma b in k2 minus 0, right? Because again, I also don't want here. So here p is non-zero, and here also this k2 is non-zero. Sorry, this element a comma b in k2 is non-zero. So I have this. But at the same time, note that whenever I choose this a comma b, the ideal corresponding to a comma b and some lambda times a comma b will be same. Okay, so that's why, I mean, let me write here. Yeah. So note that if I have, so note that ideal generated by ax plus by is equal to ideal generated by lambda ax plus lambda by. Okay, so, right? So here k2 minus 0, that is okay, but with we have to identify these ideals where we get unique. So corresponding to each p, I just want one tuple AB in K2, which will correspond to my prime ideal. Okay, so this I have to define this equivalence relation here, that AB is related to lambda A comma lambda B, where again this lambda is non-zero, where let me write it explicitly, where lambda is such that A comma B is related to lambda A comma lambda B, and lambda is non-zero again. Okay, and lambda non-zero in K. So therefore this P in Proj S, Proj A comma Y, not this. No, this was the earlier one was correct. Is one-to-one correspondence with AB to this K2 minus 0 corresponding to lambda defined as earlier. Again, let me write here. Lambda A comma B, lambda non-zero in K. So, and in so what this is here. So let me just, what is this? But if you look at this is P1. Okay, this is how the this projective space is defined, that K2 minus 0 quotiented by lambda, where A comma B is related to lambda A comma B, and 0 lambda in K. Okay, and in so if I want to get the information of Proj Kx comma Y, it is this P1 union my zero ideal. When I write this P1, it means it these are all prime ideals here. Is this okay? Like how we got this? So P Projes here, okay. It was height 0 and height 1 element. Height 0 was only 0 ideal. Okay, and height P, we got this one-to-one correspondence with P1. Okay, and in general, Pn is also defined like this. So Pn is Kn plus 1 minus 0 with this equivalence relation, again where A1 to An plus 1 is identified with lambda times A1 to An plus 1, and again this lambda is non-zero in K. Is this okay? So this is what we needed actually, and we got it. Is this clear? So the Proj of Kxy is equal to this P1 union. This is, when I write this, this is actually ideal 0. Is that okay? Ideal generated by 0. And here when I was writing this 0, this was actually this element 0, comma 0 in K2. And here when I write 0, it means this is 0, comma 0, comma 0 k n plus 1 times. Sorry, n plus 1 times. Is that okay? Please let me know if there are any doubts. This was actually straightforward information we gathered from the height of my ideal and how the height 1 prime ideals are, yes, uh, principal ideal in UFD. And we obtain everything from that point. Okay, so I hope this much was clear. Let us move to next question now. Let R be K X Y Z with standard grading. And I is ideal generated by y square comma xz. Then the dimension of this was actually true or false. So let me write it here. True or false. Then dimension of this Proj R mod I is 1. Is 1. Yeah. This is the question. I is given and now I have to find this dimension of Proj R mod I. Can you guess what it will be? So note that we have this result in general, that dimension of Proj R mod I, and this is I is also homogeneous ideal here. So defining Proj is not a problem. So I is generated by homogeneous element y square comma x z. So yes, is equal to dimension of R mod I minus 1. Okay, this is true in general. Okay, so we will be using this, or we can also find this dimension of R mod I directly also. So first note that this dimension of R is 3, right? It is polynomial ring in 3 variables. So dimension of R mod I is 3. And dimension of R mod I will be what? It is if I want to find dimension of R mod I need to find the height of R mod I in quotient ring. So I is what? I is y square comma xz. So it is y comma x, y square comma x, intersection y square comma z. So associated primes of I are this y comma x, comma y comma z. Okay. And these are also minimal primes of I. And if any ideal which is maximal over this, then it will be of this form. It will be some y comma x comma z minus alpha, or it will be x comma y comma z minus alpha, or x comma y comma, are we yo? And here it will be some z minus beta. This contains this x comma y, and this will also be x minus beta y comma z. Okay, so this is my height 0. There is no prime ideal below that which contains I, and this is 1. This is 0, this is 1. So therefore dimension of R mod I is 1. Okay, and therefore by this result here, dimension of Proj R mod I is equal to dimension of R mod I minus 1. So this is 1 minus 1, and it is 0. And if you don't want to, go for uh, R mod I, we can directly go for Proj in R. So note that the minimal prime ideals here still remains the minimal prime ideal when I look for homogeneous ideals to find Proj. And x comma y are homogeneous ideals, so they are still minimal prime ideals of R mod I when I look at them in Proj of R mod I. And the only maximal ideal which is bigger than x comma y is x comma y comma z, but which is again the maximal ideal generated by variables, but we don't consider that ideal when we find the Proj. So inside Proj, the ideals, the chain of prime ideals in R mod I is only this ideal, this minimal ideals, x comma y and y comma z. These are prime ideal, and these are the only, what I can say, these are the prime ideals, and these are the only minimal prime ideals when I look at them in the Proj. So therefore the height is 0 for this Proj R mod I. I hope that is clear. We can also we can see that the minimal primes, I is 0, that is okay. This 0, I is 0 in here. And we have this xy, and they are contained in this x comma y comma z, homogeneous in Proj, therefore homogeneous. Okay, but we don't look at this. We don't consider this ideal in when I see the chains in Proj. So this is 0, and again 0 is not. So this is R mod I is no more a integral domain. So 0 is not a minimal prime ideal. So in fact it's not a prime ideal. So this is my P1, and this was supposed to be my P. This is my P0, and this was supposed to be my P1. But this we don't consider in Proj. So that's why the only possible chain is this minimal primes, chain of minimal primes, which is, sorry, in R mod I. Similarly here y comma z. I hope what, again this will be my P0, and here we are not considering P1 again. Okay, is that okay? Since we are in monomial ideals, finding minimal primes is not difficult task. So we just obtained that and we saw that the only possible chain, it just the singleton primes and so on. I hope that is okay. Please let me know if okay. Okay. So we'll move to next question now. Yeah. Question 3, that again let K be algebraically closed field and R is this polynomial ring over K and I is my this ideal. YW minus XZ. Then true or false. So this is false, okay? Just so we know. Here they said that dimension of Proj is 1, but it's not. We got that dimension of Proj is actually 0. I mean 0. So it was false. Now the true or false for this, that Proj R mod I intersects the open set Uy. So this Uy is open set in Proj R mod I. And how we define this Uy? Uy is this, all those P in Proj S, Proj R mod I, such that, sorry, Y is not in P, and that's okay. Yeah. So this is the question. We have to check whether this Proj R mod I. So these both are subsets of spec if we see, and we have to check whether this Proj R mod I intersects U or not. Oh, here this is in Proj of S. This is in Proj of R. Oh yeah. Ui is in Proj of R and this is Proj of R mod I. So these are in a way subsets of Proj of R if we just as an identification if we see. Is that okay? And we also have this thing, if you remember, we did this in the first, I mean, before we start doing the first question, that this Proj R mod I is V of I. And when I talk about V of I, it is in Proj R. So we already have this thing. Proj of R mod I is actually isomorphic to V of I. And let me just write this definition again. It is all those P in Proj R such that Y doesn't belong to P. So any guesses here? One more thing before we move ahead with this question, note that if R is n-graded, okay, polynomial ring, and I is ideal in R, then I star, we have defined this, right? It is largest homogeneous ideal inside I. And also, second thing, that if P is a prime ideal, then we have this, that P star is also a prime ideal. So using this thing, that P is a prime if and only if P star is a prime. I mean, not P star is a prime. and this is not, this is the correct way. P star is contained in P. Okay. So what this says that if P is a prime ideal if the P star, that is the maximal homogeneous ideal contained inside P, is also a prime ideal. Okay, so that is the result we have. So using these two things, we can observe that the minimal prime ideals in a graded ring is always a homogeneous ideal. Can you see this? That the minimal prime ideal in a graded ring is always a homogeneous ideal. Why this is the case? Because since, see, P is a minimal prime. Okay, so P is a minimal prime. Okay, so and by this we have this P star contained in P, and P star is a prime. But P is a minimal prime. So if there is some prime ideal contained inside P, then that prime ideal has to be equal to that P. Okay, so let me write this here. So this implies that P star is P since P is minimal prime. Is that okay? So if I have some minimal prime ideal in a graded ring, then it has to be a homogeneous prime ideal. Is that okay? I hope that is okay. Please let me know if not. So we have to check whether this intersection. So they have asked that project Proj of this R mod I intersects the open set UI. So suppose they are empty. The intersection is empty. This UI intersection VI is empty. Then this, by definition, what does this imply? That for all P in, for all I, okay, for all P in spec R, P, or let me tell, for all I containing P, if and only if Y belongs to that P, right? And this is not the correct way. But yeah, if I is contained in P, or let me write, for all, how to write P in, what I can say, spec or proj. We are in spec actually. Spec, or let me just write, for all prime ideals, or let me just write this. P, I contains P, if and only if this Y belongs to P, P prime. Is this clear? I mean, from this definition, UI intersection VI in is empty set implies that if some prime ideal is here in VI, then that prime ideal is not here in UY. So what are prime ideals in Uy? It is all the prime ideals which does not contain Y. But that intersection in empty, so this Y must contained in this. And the moment I have some ideal, prime ideal in Uy, it means what? That Y does not belong to that prime ideal. And since the intersection is empty, this, wait, then this I won't be contained inside P. So the negative of the contrapositive of that statement will hold, which will give me that I is contained P if and only if I belongs to P and so on. Okay, so but what is my I? My I is this U, what is it? YW minus XZ. Okay, so if, so note that if I is, what are minimal primes of this I? I want to talk about the homogeneous prime ideals. So minimal primes of this ideal are y comma x, y comma z, w comma x, w comma z. You can check this. These are the minimal primes of this ideal I, min of I. Because no proper prime ideal other than this will contain, and I mean this you can check. So note that if I choose this, I is contained in w comma z, which is some prime ideal. This ideal will be in Vi, but Y also doesn't belong to this prime ideal P here, right? Y is not there in this prime ideal W comma Z. So this condition does not hold in this case. And similarly, if I take this prime ideal Y comma W, Y belongs to this ideal Y comma W, but I does not contain this ideal Y comma W, or just Y I can choose, doesn't matter. Is this okay? So this condition, which was here, that if the intersection is empty, then this condition should follow. But we can see that this condition does not follow. Okay, so this intersection is not empty. In fact, this ideal here belongs to this. So this W comma Z, this belongs to Uy intersection Vi. Is this okay? In fact, Wx also is that kind of. Wx also belongs. So therefore, this is false. In fact, sorry, this is true, that it actually intersects. So this is true because yes, it intersects and we actually found the element what it is. Is that okay? Like how they are intersecting? We are just looking at the minimal primes. And in homogeneous setups, minimal primes are what I can say, homogeneous. So here this x, y, y, z, all these are homogeneous ideals. So, okay. So we'll move to now next question. Hmm. So let x be a projective variety in P5K. So this P5K is this projective space P, P1, P2, Pn, which I defined earlier. And this K here denotes the, so we had this Kn plus, I mean here K. So the tuples, so the Kn which we considered is this K here. So they are just specifying what is the field. For example, if I write this PR5, it means that I'm taking R6 minus 0 and quotienting it with respect to that. If I take PC, then I'm taking this C6 minus 0 and under that equivalence relation and so on. So this K actually just specifies what field we are talking about, like over which field we are taking this projective space and so on. Okay, so that's it. And X is a projective variety in this P5K. And suppose Hilbert polynomial of X is P2 plus 3P4. Okay, then we have to give the description of X. And what does that imply? That is, we have to give an information about how the, what I can say, this is variety, right? So it will be with respect to some ideal I. So how that ideal I looks like, we have to give some information about that I, how the generating elements or how the relations of that ideal I looks like. Okay, so since this is about homogeneous polynomial, sorry, Hilbert polynomial, uh, we have this remark from the lecture, and I'm just we need to use that here. So if I is in some S k x naught to x n, I be a homogeneous ideal in S with degree of Vi is multiplicity of Si. Multiplicity of S mod I is, in Hilbert series, we can write it in the form of some Qm quotiented by this 1 minus Td of that form. And that, what I can say, that polynomial which we get when we evaluate that polynomial at 1, we get that multiplicity. I hope you remember the definition of multiplicity. And if dimension of Vi, so when I say dimension of Vi, so Vi is a set of prime ideals. So dimension of Vi means the size of maximal chain of prime ideals in Vi. Okay, it's D, and it is if and only if dimension of S mod I is equal to D. Okay, this is clear. I hope you can understand this. Dimension of Vi is equal to dimension of S mod I. Then the Hilbert polynomial of S mod I is of the form summation I from 0 to DEIPI, where this ED is greater than 0, and this ED is actually degree of this variety. Okay, so this is anyway given in the lectures. Okay, and here our Hilbert polynomial is what? It is P2 plus 3P4. P2 plus 3P4. And this P4 and P2 are what? This, if you remember, we defined it, I think, last lecture or a lecture before that. This Pi is X choose I. So it is polynomial defined like this. So just the formula of X minus Xi, we are just evaluating, not, yeah, X minus I and so on. So I hope you remember what that formula is. This Pi is just this X choose I and so on. So that's okay. What I was saying, yeah. So we have to find this P2 plus 3P4. So this D here goes till 4. So therefore, this D is equal to dimension of, in our case it is, so polynomial ring is not specified. So we also can call it S. S mod I is 4. Dimension of S mod I is 4. Is that okay? And also, since the variety is in P5K, so here we have 5. Therefore, this dimension of S will be 5 because S will be my K, X naught 2. Wait. Oh, okay. We are in Proj, so dimension of Proj S is 5. Is this okay? Dimension of polynomial ring X0 to X5 is 6, but the dimension of Proj S is 5 here. And here, so dimension of Proj S is equal to dimension of this S mod I plus height of I. So this give me, this is 5 is, and this was dimension of S mod I was 4 plus this height of I. So this implies height of I is 1. Again, we have this height of I to be 1. So therefore, I will be some ideal generated by a single polynomial. Is that okay? And since here also this coefficient is 3, this ED, so this E4 here gives the degree of variety. So this, where it is, this X is, we can say, defined by a cubic polynomial, degree 3, homogeneous. Okay, so this F is this degree 3 cubic homogeneous polynomial. Is that okay? So we had to find this dimension of S mod I using this information here. So we are in P5K and the polynomial goes till 4. So we got information about dimension of S and dimension of S mod I. And then from this formula, we got the height of I. And yes. Mhm. Yes. And using that, we got that height of I to be 1, which help us to obtain the information that I is a principal ideal. And this coefficient here gave us information about what will be the degree of that polynomial F. Is that okay? Okay, we have. And now recall these things from the lecture, which we will need in next question. That, yes. So this is note or recall that if S is k x1 to xn, then ideal I inside S, then this Z of I, this is zeros, right? Zeros of I is f of A is equal to 0 such that f is any polynomial in my ideal I. And similarly for this Z, I get, I mean, if I have a set in Kn, I get corresponding Vi. So all these primes in spec S such that, not, so I'm defining something else here. Vi is all these primes in spec S such that I is contained in P. So in spec S, the prime ideas, so if I look at spec S and a ring of polynomials, so here when prime ideals, so if I see that spec S is when my corresponding prime ideals are analogous to a functions or the polynomials in my polynomial ring. Okay, so if, so spec S and here S, here P in spec S, here F in S. Okay, they are like elements of these two sets. So if we have this A in S and P in spec S, then we can define this map F, not F, let me call this phi, from S to this disjoint union S mod P, such that this A goes to A bar here. This disjoint union runs over all the prime ideals here. So this is disjoint union of S mod P and P in spec S. So V of this element A is exactly all those A in, it is like P in spec S such that A belongs to P, and that is exactly kernel of this P, right? Okay, so the, I mean, kernel of P, yes, kernel of P, okay, not exactly actually. I mean, it's actually looking at where this coordinate becomes 0 under this map P in S mod P. Okay, so this is disjoint union of S mod P. So I just wanted to show this, that we can get the information about this V of A through this map P actually here. So from S we can go to this disjoint union of S mod P and see how this A goes to in S quotiented by those P, the disjoint unions, and the sections where we get them to be 0 are exactly the prime ideals which belong to my variety of that element A. Okay, so I hope that is clear for now. Let us move to next question. This is the question for which we need to do. So let P be a prime ideal of k y1 yn is equal to R, and S is this prime ideal with one extra variable yn plus 1. So let Q be the homogenization of P. Then we have to check this true or false. That dimension of S mod Q is equal to dimension of R mod P. So any guesses here? We have to find, we have to check whether this dimension of S quotiented by Q is equal to dimension of R quotiented by P. So in integral closure case which we had, in that case it was equal, but here my S and P are completely uh, different. So my R is this polynomial ring in n variable, S is this polynomial ring in n plus 1 variable, and Q is homogenization of that this given ideal P. Okay, so this statement is actually false. Okay, and the correct statement is this dimension of S mod Q is actually dimension of R mod P plus 1. Okay, and what we are going to do is dimension of S mod, and this is there, and also we have this information. Dimension of S mod Q is equal to dimension of S mod Q plus 1. This we know anyway. So if we can kind of, what I can say, relate these two terms, then we can conclude this. So we have this map phi defined in the lecture from S to R, uh, defined from the lecture, that yi going to yi for 1 less than equal to less than n, and here my yn plus 1 is going to 1. If you remember, this is the map which we had defined in the lecture. And we have And we have also concluded in the lecture that this S mod Q to R mod P, we can have information that homogeneous prime ideals in S mod Q are in one-to-one correspondence with prime ideals in R mod P. And this, for that too, this P here, this phi of Q is actually P. Then we have this condition. So phi is this map yi going to yi, and yn plus 1 is 1. And this phi of Q is P. Then I have this S mod Q to R mod Q, and the prime ideals in R mod Q are in one-to-one correspondence with the homogeneous prime ideals in S mod Q. Okay, so if and in the lecture we also have this, after defining this map, that spec of R are in one-to-one correspondence with the yn plus 1, if you remember properly. And this is open in in Proj of S. This is, I think, in lecture, I think lecture 53, yeah, 52, 53, I guess. You can see this. This is exactly what is written there. Because this yn plus 1, this becomes unit under that map. Okay, so therefore this yn plus 1 becomes the Proj, because we are not, I mean, this yn plus 1 is going to be unit under the map. So this actually becomes the equality in this case, once I have this yn plus mapping to a unit. So using all this information, we get that spec R is equal to Proj in fact. So, but in our case, we are in this setup, S mod Q and R mod P. So here spec of R mod P are isomorphic to Proj of S mod Q, yes. So once they are isomorphic, their dimensions are going to be equal. Dimension of R mod P is equal to dimension of dimension of R mod P is dimension of this spec R mod P. That is not the problem. And this is equal to dimension of Proj S mod Q. And so therefore this dimension of S mod Q is equal to this dimension of, because we know dimension of S mod Q is equal to dimension of Proj S mod Q plus 1. So, but this dimension of Proj S mod Q is equal to this. These two things. This is equal to this. Okay, but yeah, plus 1. So in this, we actually got this just by this map V, and how the prime ideals in S mod Q are in correspondence with the R mod P. And we actually obtained this here, if you notice this, and then this is actually isomorphic to this here. Any doubts? This map and all these results used here are actually discussed in the lecture. So I hope this is clear. We are just using that map P which was defined in the lecture, and this information here, that spec R is in one-to-one correspondence with the uyn plus 1 in Proj S. But uyn plus 1 is going to unit under this map phi. So this actually becomes the entire ring. I mean, this entire Proj is, and so on. Is that okay? Please let me know if there is a problem. Otherwise, I will move to next question. Okay, so if there are any doubts, please let me know. Otherwise, I will move to next question. And now this next question, 6 true or false. Yes. So we have this R is equal to K W X Y Z. Be the given be given the order with X greater than Y greater than Z. So R has just graded lexicographic order. Then this S of XY comma WZ. So I hope you remember what this S is. This is S pair of these two polynomials here, which are just monomials, gives the Syzygy omega, sorry, WZ XY minus XY WZ is equal to 0. We have to check whether this is true or not. So before, I hope you remember the definition of this S polynomial. So S polynomial, we'll see the definition of all the terms here. S polynomial of f comma g is denoted by this f comma g, and it is LCM of this initial term of f, initial term of g divided by this CF, C coefficient of leading term of f into in f minus into f minus again the same term but with g. LCM of again this in f comma in g quotiented by Cg in g into g. Okay, this is the definition of my S polynomial. And what is Syzygy? Syzygy was defined in last week's lecture. I mean, the week 10 lectures. So it is that if f1 to fm are in R, which is polynomial ring, x1 to xn, graded and homogeneous. So these f1 to fi's are polynomials in k x1 to xn. They k x1 to xn is graded and these polynomials are homogeneous. Then a CGG of f1 to fm is an R linear relations such that summation Ri Fi I from 1 to some Fm is 0, where Ri are in R. So this is the definition of CGG. It is just a collection of all these linear combinations, R linear combinations, such that summation Ri Fi becomes 0. So this is CGG. And what they are saying is that these are two, so my F1, F2 here are this, XY and WZ. And what they are saying is that CGG for this set of two polynomial is actually can be obtained from the S polynomial of this pair. Okay, so what is S polynomial? So let me call F is equal to XY and G is equal to omega Z, not WZ. Then S, F, comma G is again LCM of XY, comma ZW divided by XY. CF is just 1, the coefficient of leading term. So here polynomial F and G are just monomials. So leading term is that polynomial itself, okay, into F, which is XY, minus LCM of again XY, comma ZW divided by WZ into G, which is my WZ. And if so LCM of XYZW is just XYZW divided by XY into XY, minus again here LCM of XYZW is XYZW divided by this WZ into WZ. And if I just simplify this, I get it is ZW or WZ into XY minus XY into WZ, and which is 0. So, and also the CGG is and to calculate the CGG, what we have to do is we have this map epsilon, if you remember. So if I consider this ideal I generated by XY and ZW or WZ, doesn't matter. It has two elements. So in order to find, if you remember this week's lecture, we have also obtained that the kernels of these epsilon maps are also CGGs of ideals generated by those F1 to FMs. So to find the CGG, we actually have to find the kernel of this map. But kernel of this map epsilon is just XYE2 minus WZE1. Okay, so the similar expression which we got here, this, this is similar to what we have. So here XY, yeah, XY has, E1 is going to XY. Here coefficient of XY is WZ. And here E2 is going to WZ and coefficient of that is X2. So this is essentially the same thing with the negative sign, but that doesn't matter. If I switch this F with the G and calculate this, I will get the same thing. So that doesn't matter here, but understand that this S polynomial is actually giving us the CGG for this two polynomials, XY and WZ. Okay, and we can also calculate CGGs using Macaulay tool. Okay, so let me share the screen for that. I will show how to do that. Is this visible? Macaulay tool screen, I hope. Let me define this. W, X, Y, Z with monomial order relay. Okay, we have to write it again. So S was this polynomial ring in 4 variables W, X, Y, and Z with monomial order graded lexicographic order. So the LCMs and initial terms which we calculated are with respect to graded lexicographic order. Okay, we can't actually define initial terms and everything without the order on without giving order to the polynomial ring. Okay, so this is my S, and I just define this ideal X star Y, comma W star Z. Okay, and to find CGGs, we just have to give this command CGG of generators of I. Okay, and this is what we got. This is WZ minus XY. Okay, and in order to have CGG work in Macaulay 2, the input must be matrix. Okay, let me just write this CGG of I. It gives me error. Okay, so to find the CGG in Macaulay 2, we have to have I to be consider. I mean, we have to provide the input as a matrix. So that's why instead of writing just CGG of I, we wrote CGG of gens I, because what gens of I does, it just converts the generators. I mean, the generators of ideal in forms of matrix, and then that gives a matrix input to the function CGG. Okay, so if you want to define, I mean, apply CGG to certain input set, it has to be matrix, or we can just define this M to be matrix X star Y. Let me see if this works. Z star W. Okay, this is my matrix, and then I find the CGG of M, and I get this. It's the same thing. WZ minus XY, WZ minus XY. Okay, so either you define ideal and then use this CGG gens I, or you just define this matrix where first row is all the generators of my ideal I, and then apply this function CGG on my, on this ideal. Is that okay? That's it for CGGs. I just wanted to show that yes, CGGs can be obtained using this Macaulay 2 for polynomial rings. And we have to give input as a matrix. So either you define ideal, then apply CGG on gens of the generators of I, which in Macaulay 2 gives us output as a matrix, or you define a matrix M with all the entries in the first row as generators of that ideal I, and give that as an input to CGGs. Okay, so let me get back to here. Okay, so we'll go back to, yeah. So if there are any doubts, please let me know. Otherwise, we will move to next question. Last week assignment. Okay. In Macaulay 2, assignment question 7. What was it? I need to check. Okay. So it is the question 7 from the assignment or Hilbert series. Okay, let me check the question. Just a second. Yes, question 7, 10. Oh, yeah, this week's assignment. Last week, question 7. Okay. Okay, so you want to find so Hilbert series of this ideal. So your question is okay. So let me solve this for now. So week 10 assignment question 7 is let R be K U V X Y, and please let me know if this is the correct what I can say. This is the correct question which I'm writing here. Yeah. I is my UV, J is XY, and the Hilbert series. Just a second. Yeah. The Hilbert series of, so you want to find it in Macaulay too. R mod I intersection J is what? Right? So it is 2 by 1 minus t square minus 1. Uh, okay. Okay. And we have to check for true or false. So before going to Macaulay 2, this 2 by 1 minus t square minus 1, what this is? This is 2 minus 1 minus t square whole divided by 1 minus. I'm just simplifying it because Macaulay 2, if we remember last time, when we tried to find this, what I was saying, yeah, when we tried to find Hilbert series of a field QQ, it gave me the expression of 1 minus 3t square plus 3t minus t cube divided by 1 minus t cube, if you remember. So that's why I'm just simplifying this 1 minus 1 minus t square minus, what is it? 1 minus 2t plus t square divided by 1 minus t square, which is 1 plus 2t minus t square by 1 minus t square. Okay, so this is what we have, right? And we have to now calculate it in the Macaulay 2. Just a second. Let me share the screen here. Question is correct so far, right? Yeah, so we have to find it in Macaulay 2. Just a second. I hope the Macaulay 2 screen is visible. Yes. So, yeah. So how to, let me clear everything to avoid the overlapping of variables and so on, and let me zoom out a bit. Yeah, so my ring R is, yes, there is it. Sorry for this. Yeah, R is QQ X UV X Y. Yes, and I is ideal U comma V, and J is ideal X comma Y. right? Yes. So now we have to find Hilbert series of intersect I comma j. Right? We have to find Hilbert series of intersection of I and j. That's what I'm trying to find here. Okay. It is showing me this. And what was the answer given in the lecture? Let me check it. They are saying that it is true. Okay. 1 minus t power 4. Okay. And what did we calculate? We calculated it to be this. It is 1 minus 4t square plus 4t cube minus t power 4 by. So if we multiply and divide, so let me just do this here. Define this as to be q t. Let okay, and we see this polynomial multiplication 1 plus 2t minus t square star 1 minus t star 1 minus t, right? Because in the question we are given denominator to be 1 minus t square, but here in this expression I am getting denominator to be 4. So let us check whether this is true. And this is exactly what it is. So it was just simplification needed. Okay, so this polynomial 1 minus 4t square plus 4t cube minus t power 4 is exactly what the polynomial was in our case, which we obtained. So this is exactly the question. So question was just simplification of what was given in the. So yes, it is true. And the polynomials are exactly same. I mean the expressions which are given. So whatever denominator which we got by simplifying, when I'm multiplying it, when I multiply it by 1 minus t whole square, it gives me this polynomial here. So is that okay? Let me just check what you are writing in the chat. Yeah. Is this okay now? So, I mean, could you please let me know if your doubt is clear? What we had, what we obtained after simplifying the expression given in the question is this polynomial divided by 1 minus t square. But when I calculate this in Macaulay 2, since the polynomial ring is in degree, I mean, it is in 4 variables, it is giving me this general form. Okay. And here I have 1 minus. Yes, okay. Yeah, 1 minus t power 4. So to get this both the form equal, I just multiplied this to be, so in our expression, I'm just multiplying and dividing it by 1 minus t whole square. And I'm actually getting this exact Hilbert series which we have here. Is it okay? So the question is correct, and whatever we have got is, I mean, the answer is true, which is also correct. Okay, so okay, great. So I think we'll go back to our question again. Yeah, so just to have this when we multiply and divide it by, we just had to do this. I'm just writing for the 1 plus 2t minus t square into 1 minus t square divided by 1 minus t power 4. Okay, and whatever expression we get is exactly the expression we obtain in Macaulay 2. Okay, for Hilbert series of I intersection J. I hope this is clear. So we'll move to next question. Question 9. I think it is question, I don't remember the number. Question 7. Yeah. Question 7. Or let me just write it question 8 now. So let R is equal to K X Y Z and I is equal to xy comma y square comma xz. Then find the minimal presentation for minimal presentation matrix of I. Okay, so this is the question which is asked. We have to find the minimal presentation matrix. So if you remember, minimal presentation matrix we already studied in previous lectures few weeks back. I mean, in fact, the initial first few lectures we did that. And if you remember how it was defined, I mean, it was like if uh, R is RB Noetherian ring. I don't remember whether it was Noetherianness of a ring was needed or not. I think yes. And if M is finitely generated, what again? Finitely generated R module and generated by say M elements, then this if uh, then there then we have this surjective map from Rm to M, and if kernel of this map, we call it epsilon, is finitely generated, then we say that this M has finite representation, something of that sort. If you okay, M has finite representation, and this the map. So it is like this. So Rm to M we have, and again the kernel is finitely generated. So kernel epsilon is here. We have this inclusion, but now again this is finitely generated. So there exists some n, such that again from this Rn to kernel epsilon, we have this surjective map. And the matrix, so this is now map here from Rn to Rm. So there will exist some matrix from Rn to Rm, Rm to Rm cross n. Yeah, this matrix, and this matrix here is called as presentation matrix. I mean, we did this in previous lectures. So here we want to find this presentation matrix of this I. So R is kxyz, that is given. R is kxyz and I is xy, y square and xz. Okay, so this is given. So I is anyway finitely generated ideal over R. So it is finitely generated module. So that's not a problem here. So now I want to define this. Since R has these three generators, I have this surjective map from R3 to I. When I write this R3, it is just three copies of R. And if I denote the generating term to be E1 into E3, then E1 is I'm sending to XY, E2 I'm sending to Y square, and E3 I'm sending to XZ. So now I want to find kernel of this map. This is my map epsilon. I want to find kernel of this map. So can you guess kernel of this map? Kernel of this map is, this is Y square, by the way. This is 2 and this is Z. So can you see some obvious relation which will give me kernel of this map epsilon? So here I have xy, y square and xz. So here xz and xy. So if I multiply this by z and multiply this by y, then the subtraction will give me 0. So what it is? It is z e1 or y e3 minus z e1. Okay. And similarly, here I have y square and here I have xy. So if I multiply this by y and multiply this by x, then I get this xy square and xy square again. And here the relation becomes x e2 minus y e1. And there are no further relations which we can obtain for this kernel, right? So kernel of this map is just ideal generated by these two, y e3 minus z e1, comma x e2 minus y e1. It is like ideal generated by these two terms. So since we have these two terms here, I have this map from R2 to kernel epsilon, because now kernel epsilon is again a finitely generated module over R generated by two elements. So I get this from R2 to what I can say kernel epsilon, a map, and I have to find this, what this is here. So it is like F1 is going to this y e3 minus z e1 and F2 is going to x e2 minus y e1. So I have to just find this map, how I can define this. So R2 is going to R3. So it is F1 is going to y e3 minus z e1. So y e3 minus z and x e2 minus, I can just send it otherwise, x e2 minus y e1 and y e3 minus z e1. Then my F1 is going to, the e1 coefficient is y, e2 coefficient is x and 0, sorry, y minus y, x and 0. E1 has coefficient, this is E1, E2, and this is F1, F2. And corresponding to F2, I get this minus z, 0, and E3 has y. So my matrix M is actually this matrix. this minus y x 0 minus z 0 and y. Okay, so this is the presentation matrix which we wanted to find. Is this okay? How we obtained this? I mean, we can also, if you remember, we also obtained this presentation matrix and in Macaulay 2 for a function. So we defined this function from R3 to R1 and then if you remember, we just had this presentation of matrix and image of n and that give me presentation map. If let me just quickly show it to you in Macaulay 2 how it is done because it's been long since we did that. So let me just share this screen to see how to find this. Yeah, I think my screen is visible now. Let me clear all everything. Okay, and now these are all module maps. Okay, so we again now define this R to be what is the thing? Yeah, let me see it here. X, Y, Z. X, Y, and Z. And now I have to define this map from R3 to R1, right? When I write this I, I'm looking at it as one copy of R and so on. So in order to obtain this presentation, or I can just define this matrix to be M to be matrix X star Y, comma Y square, comma X star Z, and it is there, and N is image of this matrix. Oh, sorry, N. N is image of this matrix, and now presentation of this N. And this is the exact same matrix which we obtained, minus y x 0, minus z 0 y. And in terms of function also, I think we can obtain uh, these maps. But in C, so I is considered as, so we are going from R3 to R. Okay, so it is R3 to R. Yeah, R is, we can't write just R here because when we write just R, it considers it as a polynomial ring. Let me show you that also. So when I write R, it is giving me a polynomial ring. Okay. And when I write this R1, it is considering R as a R module. Okay. So when we define a module map, even when we are considering only single copy of R, in Macaulay 2, we have to write it as R power 1. I mean, this R hat 1. Okay. So we are again in R and we have this and we define this map to be, and again in normal ring map, in the bracket, we just put wherever the elements are going. But in module map, we have to give input as a matrix. And the map was from R3 to R1, but in Macaulay 2, when we write the code, we have to write domain first and codomain later. So it becomes X star Y, comma Y square, and now X star Z. Okay, and let us see what it is. and this is my map, and kernel F is this matrix, which is exactly what our presentation matrix was. Okay, so there are multiple ways to define a presentation matrix for an ideal, or just some element in, because see, CGG's, this kernel epsilon which we were getting in the minimal kernel epsilon which we were getting is actually CGG of that ideal I. Okay, so uh, it anyway has not matrix representation, but yeah, I mean it has that um, so, and which are CGDs can be defined for just element of a ring. So let us see what is CGG of this X star Y. CGG of gens of ideal. What is this ideal? X star Y, Y square, X star Z. It is the same ideal. Okay, so this presentation matrix which we had is actually the CGG of this ideal. Okay, so the kernel epsilon which we were talking about, um, it is the same as obtaining the relation which we obtained here. This y e3 minus x z e1 and x e2 minus y e2 are actually the CGGs which we obtained for this ideal I. So this kernel epsilon, the minimal representation matrix, and the CGG matrix. So CGG is what? CGG is a linear combination, R linear combination. So when I have this 3 cross 2 matrix, so it is, sorry, so it is R linear combination. How it works? It is minus y f1. So f1, f2, fm, if I have my my generators of I, minus y f1 plus x f2 plus 0 f3. And second CGG equation is minus z f1 plus 0 f2 plus y f3. So those two equations are just represented here in the matrix form. And that same matrix, and the CGGs, the coefficient, when I write it in terms of matrix, gives me the presentation matrix of that ideal I. I hope this is okay, like what I'm trying to say here. So the CGGs or minimal representation matrix, the first CGG and the minimal representation matrix are actually the same thing, which are like studied. Uh, it's like studying the same thing, but through different uh, sides of the same object. Is this okay? What I'm showing here? Here the CGG matrix, and here we obtain as a map also we can obtain it, the kernel of that module map, and also just by defining the generators of I to be a matrix, and then image of that, because it just wanted to have it as a module structure. Okay, CGG can't be obtained for just, I mean, this R structure needs to be there in order to find the presentation. Okay, but CGG can be obtained for a matrix, but when I want to find a representation, it need to have that module structure in it. Okay, so let me stop sharing this and share back this. So is this okay? How to find the minimal presentation matrix and so on? Okay, so I think we are anyway about time now. But yes, the questions when you try to solve, please check what it means here. I mean, This was quite easy question, but yeah. And any other questions which you have from this lecture or previous lecture, or any doubt from earlier classes? Please make, because I don't want to move to next question because it will take a lot of time, and we are already above 5. So if you have any questions, please let me know. And also, like next week, we might have one extra uh, live session like this, where we will be discussing problems from all the course. So if you have any doubts, please be prepared with it. We will be discussing all those in that lecture, and all the things which we missed during these sessions, we might discuss those as well in that problem session. But apart from that, any doubts for this week or last week's question, please let me know. Otherwise, we can end the session. Yeah, no doubts. Okay, great. You will receive the information about this next week's lecture in this week sometime, about the extra session. Yeah. If not, no question, then we can stop. Yeah. Thank you. Yeah. Thank you.